कम्प्युटर साइन्स र इन्फर्मेसन टेक्नोलोजीका प्रोफेसनल कोर्सहरूको लागि सब्स्क्राइब गर्नुहोस् टेक-शास्त्र युट्युब च्यानल। Hello students, welcome to Tech-Sastra. In this video, you will learn about the Gauss-Seidal method. Here I will be covering what is Gauss-Seidal method, in which condition we have to apply this method, and at last I will write a C program to implement the Gauss-Seidal method. So let's start by introduction first of all. Gauss-Seidal method can be used to solve a system of linear equations by using numerical approach. It is an iterative method. That means we apply a given formula in a number of iterations. Here, first of all, we make some initial guess for the variables and then make the guess more and more precise in the successive iterations. Imagine we have a system of linear equations like this, which is in the form of a1x plus b1y plus c1z equals to d1, a2x plus b2y plus c2z equals to d2, a3x plus b3y plus c3z equals to d3. To apply the Gauss-Seidal method, the given system of linear equations must have strictly diagonal coefficient matrix. That means when we represent this system of linear equations in matrix representation, it will be like this. Then this matrix a1, b1, c1, a2, b2, c2, a3, b3, c3 is called the coefficient matrix. And one strict condition for Gauss-Seidal method to apply is this coefficient matrix must be strictly diagonal. Strictly diagonal means in the first row, a1 must be the largest number. In the second row, b2 must be the largest number. And in third row, c3 must be the largest number. If that is the case, we can apply Gauss-Seidal method to solve this system and find the values of x, y, and z. In some cases, we may see that the coefficient matrix is not strictly diagonal. In that case, we can reorder the equations. That means we can move some equations upward and downward in order to get the strictly diagonal coefficient matrix. Now, after finding the strictly diagonal matrix, then we can apply the Gauss-Seidal method. And to apply the Gauss-Seidal method, we do a very simple thing. We will find x from this expression, y from this expression, and z from this expression. And then we will get the values of x, y, and z, something like this. X can be obtained from the first expression, y can be obtained from second equation, and similarly we can find z from third expression. After finding the expressions for x, y, and z like this, then we make an initial guess. We imagine the values of x, y, and z as appropriate as possible. We make an initial guess for x, y, and z, and let's call that x0, y0, and z0. The better idea is to imagine the approximate values of x, y, and z to be all zeros, where x0 represents the first initial guess for x, y0 represents the initial guess for y, and z0 represents the initial guess for z. And we will use these values of x0, y0, and z0 in the given equations to determine x1, y1, and z1, which will be the first approximated values. But here one thing is a little bit tricky. Don't put the values of x0, y0, and z0 directly in these equations. Rather, you can do a little bit tweak. That is, you can put the guesses for y and z, that is y0 and z0, in the first equation, and it will give you the value of x. But this will be x1, right? The first approximated value of x. Now, in the second equation, while finding y1, instead of using x0, you can use x1, that is already found from the first expression, because that is more appropriate value of x. So you can use this value of x1 obtained from the first expression to find first approximated value of y1. And finally, you can calculate the first approximated value of z, that is z1, by using x1 and y1. So what I told you here is clearly given in this expression. If you look at this expression clearly, the x1, that is the first approximated value of x, is obtained by using y0 and z0, which are the initial guesses. y1 is obtained by utilizing this x1 and z0 because z1 has not been approximated yet. And finally, z1 can be approximated by using first approximations for x1 and y. That means you can use here x1 and y1. In this way, you can find x1, y1 and z1. In the second iteration, you can find x2, y2 and z2 by using the same method. You will use y1 and z1 to find out x2. Then to find y2, you will use x2 and z1. And to find z2, you will use these calculated x2 and y2. Okay, and you can go on for third and fourth and fifth iterations. Okay, but how many iterations you will use here, that will be decided by our error tolerance. Sometimes if we do not have the error tolerance, then we can guess. If the similar values are repeating, then we can stop and decide the approximated values for x, y and z. Imagine we have given error tolerance to be 1%. Okay, so 1% means the error tolerance is 0.01. If you find x2 minus x1, the difference between x2 and x1 is less than error tolerance, that is 0.01, and the difference between y1 and y2 and z1 and z2, all the differences of the successive iterations are less than the given error tolerance, then we can stop and we can decide the values for x, y and z. If the error tolerance is not given, if the values of x, y and z are having very less differences in each iteration, then we can stop and decide the approximated values for x, y and z. Here I have discussed only the theoretical idea. Let's solve one real example and then probably it will be more clear to you. So imagine we have a system of linear equations as x plus 10y plus z is equals to 24, 10x plus y plus z is equals to 15, x plus y plus 10z is equals to 33. Alright, this is our system of linear equations and we have to solve it by using the Gauss-Seidal method. We have to decide whether the coefficient matrix is perfectly diagonal or not. If the coefficient matrix is perfectly diagonal, only then we can apply the Gauss-Seidal method. So here, in the first equation, the second term is highest. Let me reorder these equations. Alright, now I can apply the Gauss-Seidal method. And here you can see the coefficient matrix is A equals to, what is the coefficient matrix from here? It's 10, 1, 1, 1, 10, 1, 1, 1, 10. We can see this is strictly diagonal. So we can apply the Gauss-Seidal method. And to apply the Gauss-Seidal method, we determine the values for x, y and z. We write the expression for x from this first equation, and that will be x will be equals to 15 minus y minus z by 10. This will be the value of x. Y will be equals to 24 minus x minus z divided by 10. And finally, the value of z will be equals to 33 minus x minus y divided by 10. Now we will use these expressions in successive iterations, and before that we have to decide the initial values for x, y and z. So let x naught is equals to y naught is equals to z naught is equals to 0, let's say. So first you can write the count or the iteration, value of x, value of y and value of z. Alright, so for the initial guess, that is 0, we guessed the value of x is 0, y is 0 and z is 0. In the first iteration, x1 will be equals to 15 minus 0 minus 0, that is 15 by 10, that will be 1.5. 1.5 in the first iteration, right? Now we'll find y1. To find y1, we will put x1 here because we already found x1, which is the higher approximation, and we will use z0 over here. And by this, we can find the value of y1. Value of y1 will be 24 minus 1.5, 22.5 by 2.25. We found y 2.25. And to find the z1, we can put the values of x1 and y1, and it will give us z1 to be 2.925. Now we can find the second approximation, second level of approximations. For that we will find x2, and to find x2, I'll write here x2, and here I will use y1 instead of y2. I can use y1 and z1. I will use y1 and z1 to find x2. Alright, y1 and z1 are already obtained from here. This is y1, this is y1, this is z1. So if you use these values of y1 and z1, you will find the value of x to be 0.9825. Now again you can find y2. For that you will use x2 and z1, and you will find here y2 to be 2.0093, 2.0093, and you can find z2. Z2 will be equals to 33 minus x2 minus y2, and that will give us 3.0008. Now we'll go for third iteration, and in the same way, in the third iteration you will find the values to be 0.999, 0.999, 2.000, 3.000. So imagine our error tolerance E is given to be 0.01. That means the successive values cannot have more than this much difference. So let's check. Over here 0.99 and 0.98. So difference will be 0.01, right? Which is tolerable. And here value of y is 0.009 over here, 0.000. So difference over here is less than this, and here the difference is definitely less than this one. It's the 0. Successive approximations for x, y and z are having difference less than or equal to error tolerance. So we can stop it and conclude the final values of x, y and z as the desired approximations. So in third iteration we found the value of x to be 1. We can call it 1. And the value of y to be 2 and value of z to be 3. Alright, so our approximation is 1, 2 and 3 by using Gauss-Seidal method. Now let's go to write a C program for the Gauss-Seidal method.